Alright, this is day 30 of solving math problems like Hololive never notices me. Well, today we are going to prove pretty much that trigonometry is connected to hyperbolic functions, right? So, woohoo, a pretty interesting topic to talk about and to get into. So, first of all, let's review what we know about our trigonometric functions. So, we know that sine, cosine, tangent, all those functions, right? They pretty much relate to a unit circle, right? And if we were to say that this is on a Cartesian axis, let me just go ahead and struggle while I make this rough sketch. And we pretty much know that if we were to connect a line from the origin to the circle, right? We see that the radius is going to be 1 for our unit circle because it is x squared plus y squared is equal to 1. Well, actually, let me just write that in white so that no one is confused. So pretty much we're using our unit circle, right? And here we see that if we pretty much form a triangle, namely a right triangle, we get an angle, right? Theta. And since the green is y and the pink is the x-axis, we could use pretty much our cosine functions, right? And say, okay, we have cosine is adjacent or hypotenuse, which is x, and we could replace x with that, so we get cosine theta. And sine is just opposite over hypotenuse, and it's y, so we could say sine theta is equal to y, which from this we pretty much also could get our Pythagorean theorem, which is cosine squared plus sine squared is equal to 1. And here we can see that if we use all the knowledge, right, and look at just like this sector, like the area from this small pizza slice, the area, right, is theta over 2. So that is a cool fact. And we're pretty much going to go ahead and look mainly now at our hyperbolic functions. So let me just go ahead and draw that right here. I'm only going to draw just the right side. So let's say we want, let's say, this hyperbolic function, right? X squared minus y squared is equal to 1. Okay? So pretty much like the distance from 0 to this is 1. So yeah, like as we would say our cosine and sine functions, we are pretty familiar with them, right? Like they have a connection with circles, but like pretty much hyperbolic functions, they operate very differently. And we're pretty much like going to talk mainly about how this hyperbolic graph is connected to a circle and a triangle, right? So like as we already expressed sine and cosine in terms of x and y, now we're just going to go ahead and look at this hyperbola. And we could create like a new set of functions pretty much similar to that of our trigonometric functions, kind of like in the same family, you know? So pretty much if we try to do that, we draw a point from here, the origin, to some point onto our hyperbolic graph, right? So like unlike trigonometry, hyperbolic functions cannot use angles, right? Because they aren't trigonometric and they can't take angles as inputs. So, like, that's the main problem, right? What are we going to define all of this here? So, like, we're going to be thinking in terms of, like, hyperbolic angles, right? And it's not, like, measured in degrees or anything, right? Like, it's not like radians, degrees, any other, like, measurement of way of saying degrees. It's pretty much related to area. And if we pretty much shade in all of this, we could say that, like, the area is going to be, let's say, alpha over 2, right? Like, we're just going to use area to represent our hyperbolic angle and represent our trigonometric and hyperbolic functions. So you saw how, like, alpha over 2 kind of related to the area of this sector right here as theta over 2. Yeah, it has the same angle, right? Because if we go ahead and just try to make a right triangle and say, okay, we're going to say that we have, this is sine h of alpha over 2 and whatever. This pretty much is going to give us the area if we use integration, which we're not going to get into. So pretty much now we have our hyperbolic angle, right? And it's kind of like going to form a right triangle, right? So let's just say that this coordinate system we're going to create is the point P is cosh of, let's say, t comma sine h of t. So we're just inventing a new function, right? Without knowing anything about hyperbolic functions. So we can pretty much replace alpha over 2 with t, right? So we're just going to say that we have t. And since we already know that cosh of t is the x-axis, we could replace that with this. And we have sine h of t. And pretty much now that we have x and y, right, we see that we could also have our identity, right? And just like the Pythagorean identity, right, sine squared theta plus cosine squared theta is equal to 1. The same goes for the hyperbolic function, right, which is going to pretty much be cosh squared of t minus sine h squared of t is equal to 1. And the only thing differing from these is just the sign, right? And they look very similar. And basically, like, they are tied in the same geometry, just using the Pythagorean theorem or just putting in x and y. And the line from 0 to this point P, right, is very special, right? Because it pretty much tells us the direction of the hyperbolic rotation, right? If we were to, like, move there, or pretty much go into the fourth quadrant. If we were to move this point infinitely all the way to infinity, we could pretty much also trace out, like, our functions, right, for cosh and sine h. And, like, the further you go, the bigger the area, obviously. And yeah, that's pretty much going to say that the value of t is bigger as the area gets bigger. And the main question is, right, what is this going to do, and what does it have to do with trigonometry? Right? Like, that's the main question pretty much we're all wondering. Well, they connect in the fact that we could say cosine h or cosh and sine h, they're pretty much expressible as exponential functions like e to the x. So let's say here we have e to the x minus e to the negative x over 2 is equal to sine h of x, and e to the x plus e to the negative x over 2 is equal to cosh of x. So this is pretty much important, right? Because of the fact that like they really connect to exponentials. And if we just use one cool identity, right, that is Euler's identity, we see that e to the ix is equal to cosine of x plus I sine of x, right? And solving for e to the x in these equations, we're going to have that e to the x is equal to cosh of x plus sine h of x. And looking at our two equations, right, e to the x and e to the ix, they look eerily similar. And that's pretty much where it gets cool, right? This is where it all gets cool. Like, if we go ahead and say, okay, x, we could replace that with ix for our hyperbolic functions. We could get ix, and ix. And here we could finally relate our cosine and cosh and sine h. So let's go ahead and do that. We have cosine of x is equal to cosh of ix. And finally, we're going to have that I sine of x is equal to sine h of ix. And that's pretty cool, right? Because of the fact that we connected our trigonometric functions that arise from circles to a new type of function that arises from a hyperbola. So this is very, how do I say this, right? Very beautiful, right? Because of the fact that you're connecting something irrelevant like e to the x that has nothing to do with cosine and hyperbolas, right? Well, it kind of does have to do with hyperbolas, but like in the grand scheme of things, right? When you look at, let's say, this graph, right? A exponentially growing graph, you wouldn't say, oh, it connects to this or to this, because they are very irrelevant. But connecting imaginary numbers with exponentials and trigonometric functions pretty much lead to hyperbolic functions, and they pretty much help us in higher levels of math, right? Like, why do we care about hyperbolic functions? Like, they show up everywhere pretty much, right? From, let's say, example, hanging cables, right? And let's say special relativity, hyperbolic geometry, obviously, and pretty much like just kind of like how cosine and sine help us describe waves and frequencies and stuff like that. Hyperbolic functions pretty much help us describe exponential curves and hyperbolic curves. And pretty much like at first glance, we would say that trigonometry and hyperbolic functions are pretty much two different subjects, right? And they are like apart in two different worlds or two different dimensions, when they quite literally are, right? They're pretty much separated by imaginary numbers and the real numbers. But like they're pretty much deeply connected to like the geometry and the derivation of connecting a circle with a triangle and a hyperbolic graph with, or hyperbola with an exponential function. Pretty much they're like very connected to like specifically identities, like the ones we just found. Cosine of x is equal to cosh I of x, I sine of x is equal to sine h I of x. And they're also specifically connected through complex numbers, right? They're like mathematical cousins or siblings, whatever you call it. And one is circular, right? And the other is hyperbolic. And both are pretty interesting and beautiful to study and look into. And once you see how connected they are, you realize that circles are connected to hyperbolas, which are connected to exponential functions, which then are connected to imaginary numbers. And those same imaginary numbers tie in all those three things. They connect hyperbolic functions with trigonometric functions. So, yeah, pretty much that is how interesting they are. And overall, this was a very fun topic to talk about because I actually was able to explain why they are connected, and we were also able to prove it at the same time, right? So that's pretty much it for this video. And like in general, it was very fun to explain and prove that trig is connected to hyperbolic trig, right? So yeah, thank you for watching, and bye bye.